Well, one of the things we do every day is read AstroPH to find out what new planets, what new planet parameters, that kind of thing have come out. And this month is Calen's turn. And just to give you an introduction to Calen, every morning he has sent a pirate-themed email about today's AstroPH, which has been a fantastic way to wake up every day. So thank you, Calen. And tell us about microlensing planets.
Thank you. Thank you. Oh, it is on. So hello. Very excited to be at the Sagan. I love the Sagan. There's so many new faces in exoplanet science here. It makes me so excited. I was in your seat, I don't know which one of you, years ago, and so it's cool to be on the other side. So I'm going to talk about microlensing, gravitational microlensing. This is kind of the potpourri day, and so switching gears a little bit for something completely different. One of the ways that I always think about this is in terms of playing and winning the stellar lottery. So I'm taking a page, well, the cover, the front page out of a Philip K. Dick novel. This is the solar lottery. And kind of what we're doing in microlensing is we try to pick the needle out of the haystack. Now, I wouldn't take the analogy too far. Philip K. Dick did a bunch of coke and died relatively young. So maybe don't think about it too much. I'm also not really sure, you know, what's the microlensing? Like, is this you? Is this microlensing? I don't know. But the point is, we're trying to find planets in the haystack. And it's hard, but not impossible. So to transition from some of the main techniques that we've heard about earlier in the conference and the workshop today, just put up a couple of big exoplanet demographic questions. And all of these main discovery and characterization techniques provide insights into these and a bunch of other ones. Not all of them are accessible by all techniques, and not all of them are purely observationally or theoretically driven. And so what I want to do today is talk about exactly where observational microlensing fits into this picture of exoplanet formation, statistical demographics, et cetera, fits in. This is a beautiful picture taken by HST of the ONC, which I really, really love. So, this is a very movie-heavy talk. So just kind of to do like a Gilligan's Island recap of the first 3 days. So first, I think it was the first day, you heard about direct imaging, or maybe the second day. And this is a direct planet detection technique. So this is a beautiful animation made by Jason Wang, who's now here in SoCal, showing HR 8799, four super Jupiter planets on periods of years. And here you're actually seeing the planets themselves. It's pretty cool. People who are not astronomers, who are friends of mine, still get their minds blown when I show them something like this. Then there are indirect techniques. So everybody in here is very familiar now with transit, when you have the actual planet occulting the light from the star. And so here we're actually inferring the presence of a planet based on how it alters the properties of the host star. So in the case of a transit, you're looking at the dip in the light curve, which is telling you about the relative radii squared ratio. And then the second indirect technique, of course, is rate of velocity, which you've also heard a bunch about this week. And you're going to do some more hands-on and hear about transit plus RV fitting from Jason tomorrow. And so here again, you're indirectly determining that there's a planet orbiting the star, looking at the shift of the spectral lines periodically due to the planet's orbit. Microlensing, however, is very unique. It's not direct, it's not indirect. And I'm leaving you in the dark here on purpose. It's doubly indirect. So what we're seeing here is the light from some arbitrary star. We call it the source star, some background star. And its light rays are actually being bent, deflected due to the gravitational potential of some intervening foreground lens system. And that's what you're seeing kind of go across there, bottom left to the bottom right. And what we see from the Earth down here, oh, I was going to show it again, is actually the magnification of the light from this background source star. And that allows us to infer properties about this intervening lens system. So here we've got a pretty run-of-the-mill planet plus star. And here you see a mostly symmetric in time light curve. And this little blip here is what tells you that there's not just one body in the lens system, there's actually a planetary companion. So as Jesse mentioned, we're here at the Exoplanet Archive. So I'm going to show a couple of Exoplanet Archive plots to get us in the mood for exoplanet demographics. So what I'm showing right now is planet mass as a function of semi-major axis. These are data as of 12:13 a.m. this morning via the API query. And already you can see, kind of being blind to technique, that there's structure in this plot. the lower right corner, low mass planets at large separations, we haven't really found too many of them. Now, this folds in a lot of detection biases and efficiencies. So one of the things we want to do is figure out, what is actually intrinsic to the populations of planets, and what's something that's just, from our perspective. So we can take this one step further and actually color code these according to discovery technique. And you can see that indeed, as we all know, the different techniques are exploring different regimes of parameter space. The sweet spot for microlensing in particular is separations of about 1 to 10 AU, going off a little bit more distant, and planet masses down to and below the mass of the Earth. Now, I should say that currently of the, 3,774 planets that have been discovered, 64 have been due to microlensing, so it's about 1.6%. So it's not a huge fraction of the overall number of planets, but there are different ways, going back to kind of the demographic slide I was showing on the top of the ONC, that we can slice the data to show the utility and the power of different techniques. So here, I'm doing planet mass as a function of linear planetary system distance, same color coding as before. There are a little over 1,300 planets that have measured quantities for both of these. And again, as of this morning, so microlensing is about 5% of these planets that have system distances. But if we start asking what fraction of the systems that are more distant from the Earth have been detected via microlensing, about 40% of the planets farther out than 1 kiloparsec, and it rises to 75% farther than 2 kiloparsecs. So this is one of the strengths of the microlensing technique, and I'll talk about the others throughout the talk. Really, as an Exoplanet Archive scientist, I feel like the point here is, a new advertisement I was thinking of. So you can come to the Exoplanet Archive for the API functionality, and you can stay for the exoplanet demographic exploration. So what is microlensing? How exactly does it work? So here's a slightly more detailed animation that's showing kind of a zoom in. The blue fixed star, a fixed position, is an arbitrary source star. And we're watching as a lens system comprised of an M dwarf and some planet passes in front. And again, we get this characteristic, what's called the Paczynski curve, which is the smooth, otherwise symmetric in time light curve that's due to just the host star itself. And then you get this perturbation on top that allows you to tell that there's some additional body in the lens system. You don't know a priori if that means it's a stellar binary or a planet or exactly what's going on. We can even take a closer look. And what we're going to see here is another toy model, but we're going to zoom in on the scale of tens of micro arc seconds. And you'll see that the light from this background source star is actually split into 2 images, and that these trace out a circle, what's referred to as the Einstein ring. This is the angular scale that's common in microlensing phenomena. We can look at this schematically to get a better sense of what are the variables and what is the geometry that's actually going on. So the angle beta, so O represents the observer, this is the Earth, or Spitzer, or K2, wherever your telescopes are. L is the lens, S is the source, and I is the images. So we saw those 2 arcs that traced out the Einstein ring in the previous slide. The angle beta tells you the true position of the source. This is where we would see the source on the sky if there are no intervening masses that would be deflecting its angular position. The bending angle is this alpha hat here, and what's referred to, bending angle is alpha hat, and what we then see are images at positions theta on the sky. So you can see here it's tracing out I. And alpha D without the hat, we were running out of variables, so we had to get a little creative. That's what's called the deflection angle. And then here on the x-axis, we've labeled the distance to the lens. This is something that you can measure, and I'll talk a little bit about, and the distance to the source. On the right-hand side, we've assumed perfect observer lens source collinearity. And what happens here is, in this case, the 2 images that we saw, they actually perfectly trace out this Einstein ring. And in the case of the minimum separation of the lens and the source on the sky, you would get a perfect single image whose radius would be theta E. So this specific value of theta corresponds to observer lens source, again, collinearity, and this is the scale that we use. So we can project it into different planes. RE here is the physical size of the Einstein radius on the lens plane. And then this R tilde, again, we ran out of letters. R tilde E here is the physical projection of this Einstein radius back onto the observer plane. All right, now everybody is in like the 1% of microlensers, or of astronomers who know about microlensing. This brings us to what's called the lens equation. So all of microlensing revolves around, mapping the position of the images, which is essentially what you're seeing. Even though you can't actually spatially resolve them, the scale of the Einstein radius is tens to hundreds of micro arc seconds. So it's not something you're spatially resolving, but this is what in effect you're seeing during the event that's causing the magnification. A mapping between the position of the images, represented here by theta, you subtract that deflection angle, and then that allows you to back out what the true position of the source is. So let's look at some light curves. Here are some simulated events. These are for a microlensing event due to a single lensing mass. On the left, I'm showing the magnification. How much brighter does the source get as a function of time, as a function of a couple of microlensing parameters. And the color coding of the lines here corresponds to different source trajectories in the right panel, color coded. So what we're looking at in the right panel, we're looking from the Earth or from an observer position through an Einstein ring that is centered on the lens. Again, this is just one lensing position, and through that to a background source star. And you're watching for 10 different trajectories, left to right, what the resulting light curves would look like. And then the gray kind of ovoids are showing you the images, and there's two in the case of one body. There's a major image, which is outside the Einstein ring, and then there's a minor image, this minus, inside the Einstein ring. And what you can see, there's a bunch of takeaways here. The most, I would say, salient one is that the amount of magnification does not depend on the mass of the lensing system directly, and it does not depend on the light output from the lens host star. So this is one of the reasons I refer to it as doubly indirect. Instead, it just depends on this parameter U, which is the generalized separation, angular separation between the source and the lens and the plane of the sky. And U, if we go to the next slide, is a function of three different quantities. So there's the T naught, which is the time of peak magnification. That just tells you when that central value is hit. The Einstein time scale for events that have no blending. You can think of this as the full width half max of your smooth symmetrical time light curve. And then U naught tells you what is your minimized, what is the minimum angular separation between the lens and the source, which occurs at T naught. That's when you get the peak magnification. And so we can take the lens equation and we can actually derive what the magnification as a function of U, which is a function of time, is. And that's where this top equation comes from. And this animation will give you a sense of how the position and morphology of the images evolves throughout the course of a microlensing event. So blue are the images, red open circle is the true position of the source. So that's our beta. Blue is tracing out our thetas. And I need to start it again. And the green circle here is the Einstein ring. So you can see that the angular extent of the images is maximized when the angular separation between the lens and the source is minimized. Pause for effect. So when we add in a second lensing body, so now let's consider a planet plus a star. This is where we introduce perturbations onto the underlying, otherwise smooth magnification structure that you get as a function of time. And I know this is a scary word for a lot of people, you learn about caustics. Caustics. The fact that the adjective caustic isn't really an endearing one doesn't help. But what we're going to do here will hopefully kind of make it a little bit less scary. So there are two additional parameters that you can fit for in a microlensing event with two bodies. And this is the separation, S. So this is the instantaneous projected angular separation normalized to the Einstein radius. a shorter way to say it is this is a proxy for your projected semi-major axis between the lens star and its, the planet that it's hosting. In angular units, normalized to Einstein ring, but think of it basically as indirectly measuring the semi-major axis. And then Q, down here, is the mass ratio. This is just telling you what is the mass of the planet divided by the mass of the host star. So what happens when you start populating the lens system with additional bodies, so now you've added a planet to the star, is instead of the magnification no longer just depends on the distance, just a single parameter between the source and the lens, where it's azimuthally symmetric and so rotationally invariant. Now there's actually structure in the plane of the source that tells you where and how additional bumps and wiggles will be introduced into the light curve, allowing you to infer the presence of a planet, or at least some second object in the lens system. And these are what we call caustics. So these, in the case of a two-body lens system, are closed, non-intersecting curves. And formally, this tells you where the lens equation, which again is the mapping between the source true position and the apparent image position, where this magnification derived from the lens equation formally diverges to infinity for a geometric point-like source. That's kind of a mouthful. Another way to think about it is if you were to have a source star cross one of these caustics, that's where the light curve would go bump in the night, and you'd be able to tell that there's more than one body in the lens system. So what we're showing here in the top panel is green. Green is the Einstein ring. We've populated a lens system with a host star fixed at the origin and a planet over here. And there are three caustics in the case of close separation. So there are three topologies, and this depends on your separation between the lens, host star, and the planet in units of the Einstein radius. If your separation S is closer than one Einstein radius, this is what we refer to as a close topology. And that tells you that there are two planetary caustics and one central caustic. As your separation changes, the number of caustics you have also changes. There's always one central caustic, and there's 0, 1, or 2 planetary caustics. And so basically, if you had a source whose trajectory went like this, you would notice that there's a microlensing event, but you're not passing by any of the caustics. So you actually would not be able to tell that there is a planet, which doesn't mean that there isn't one. This is something you would rely on detection efficiencies to back out ultimately. If you had a microlensing event with a source trajectory that took you over one or both of these caustics, zoomed in here on the bottom panels, that's how you would infer the presence of a planet. Now this topology changes as a function of S and Q, these two parameters that we've added for the two-body lens system. So what I'm showing here is we're keeping the mass ratio fixed. The mass ratio is set at Q of 0.01, and we're changing the separation from a close topology, about 0.6 in units of the Einstein radius, to a wide topology. So you're seeing basically as the planet, as we just, for example lensing systems, as we move the planet, how does the number, shape, location of the caustics change? And you can see, I love this part. This makes me think of episode 8 in Star Wars. This is basically the entire plot. There's a spaceship shaping another spaceship. I thought about this last night at anyway. And so yeah, you can see in the close topology, there's two planetary caustics. When you get to a resonant topology, S about 1, they merge with the central caustic, and you have one caustic. And then as S diverges away from 1, this caustic will kind of get pinched off right there. So now you have one planetary caustic that's kind of, again, following the planet. So there's a lot of important things to note here. One is that the number of caustics depends solely on your separation, not on the mass ratio. Another is that the location of the caustics are not coincident with the position of the planet. That's a common misconception. And another is that this underlying caustic structure tells you what kind of source trajectories will allow you to tell that there's a planet, will make your light curve go bump in the night. We can do the same thing where we keep S fixed. So now this is for a close topology. We're keeping the planet and the host star together. And we're watching as basically the position and the size of the caustics changes as we increase the mass ratio. from 10 to the -5, which is about a super Earth around the sun, to 0.1, which is a 10 Jupiter mass planet around an M dwarf. So what you can see is that whereas S tells you, number, shape, and location of caustics, Q is basically telling you the size. As we increase Q here, the caustics here are getting larger and larger and larger, and it's even more easy to tell looking at the central caustic. And you can also see that for this close topology, the two planetary caustics are essentially tracing out the Einstein ring until if you were to get to an equal mass, you'd have a planetary caustic at pi over 2 and 1 below. So this seems pretty easy. We all now know everything about caustics and how to derive them and what they mean. And so finding planets with microlensing should be relatively straightforward. You just monitor a bunch of stars, you wait for a source to go over a caustic, and boom, you've got the mass ratio and the separation, and you're done. Not so fast. So if we turn to our friend, there's a strong Star Wars theme here. If we turn to our friend C-3PO, he would remind us of some of the observational challenges in microlensing. The probability, even toward the galactic center of the Milky Way, where the stellar surface density is the highest, and so the probability of getting a chance alignment of some arbitrary background source star and some intervening lens system that has a planet, even when that's maximized, the chance of any individual star being microlensed is about 1 in a million. If we were to ask K2SO, just say the odds are low, very low. So how do microlensing surveys try to mitigate this? So there's several factors that we try to balance. One is the stellar surface density. If you're looking where more stars are, one way to beat 1 in a million is to just buy a crap ton of lottery tickets. Another thing that we have to contend with is extinction. So the intrinsic stellar, the underlying physical stellar surface density might be high, but if there's a lot of crap in the way, dust and Dyson spheres, whatever's floating out there, then you don't actually see the stars. That doesn't help you. Not only that, but there's differential reddening on small spatial scales of even arc minutes or sub-arc minutes. So this drives us to a couple of features of microlensing surveys. We want to monitor a lot of stars, hundreds and hundreds of millions, and we want to have color observations to help us mitigate some of these effects. So in practice, what does that look like? So here's a zoom in of the galactic bulge of the Milky Way. And so one of the surveys, this is the OGLE survey. It's a Polish, run by a Polish group. The telescope is at Las Campanas in Chile. They divide up the central region, about 10 degrees by 10 degrees, into target fields. And they do something even a little bit smarter, because you can see there are bright spots where the stellar surface density is the highest. So they don't observe every spot with an equal cadence. So the color coding goes from clear, which is, we're not going to do that, to red, which is cadence of maybe 10 or 15 minutes. And this allows us to optimize our chances, to continue buying more lottery tickets and try to find these microlensing events. They're not the only microlensing survey. OGLE, the telescope is based here. A few years ago, the KMT-NET, Korea Microlensing Telescope Network, came online. They have 3 nodes, one on each major southern hemisphere continent. There's also MOA, Microlensing Observations and Astrophysics. This is a joint Japanese-New Zealand group, and they have their telescope down in the South Island. And then there's WISE as well, an Israeli telescope in Israel. And so between these, we've entered into an era where there's enough longitudinal completeness in the survey networks, and the CCDs and the apertures have gotten good enough where with surveys alone, you can get the cadence that you need in order to detect microlensing events, and also to characterize the perturbations you get induced by the presence of planets. In microlensing, the game isn't burrowing down into the noise of part per million signals. Often our planetary perturbations, and I'll show a couple in the remainder of the talk, are several tenths of a magnitude. More what drives us is the actual time scale. These perturbations can be maybe an hour for Earth-mass planets or a day for Jupiter-mass planets. So having this longitudinal completeness is important. So I'll show the first microlensing exoplanet that was ever discovered. So you see this, I kind of think of this as like the eye of Sauron, this two-peaked feature here. This tells you that a source star is going into and then out of a caustic. Anytime it passes over, you get a sharp spike in the magnification structure. This was an event in 2003, published in 2004, and it turned out to have about a Jupiter mass planet on about a 3 AU orbit. However, this system, to actually derive the physical parameters, all they measured, all that we get in microlensing events, just from the light curve itself for kind of a standard run-of-the-mill light curve, is this Q and S, the mass ratio and the separation. So how do we actually turn those into planet mass and semi-major axis? There are several mass distance relationships that we invoke that describe and characterize the lens system. So I'm going to go through the 3 main ones and then focus on 2 of them. So what I'm doing, describing it on the left and showing the equation with the salient observable on the right. So one's mass distance relation for the lens system hinges on measuring theta e, this Einstein radius. If you can measure that angular scale, here kappa is a constant, and the relative parallax, you can get that, and then you can determine the mass of the lens system. So in here is the distance to the source and distance to the lens. So if you assume a source distance, and since we are looking toward the galactic bulge to roughly 90% confidence, all of the stars are located at about 8.2 kiloparsecs. You can describe an uncertainty that's the dispersion of the bar. And so this just boils down to the distance to the lens, constant. If you measure theta e, now you have distance of the lens on one side, mass of the lens on the other side. And so that gives you a line in the mass distance relation space. One way to do this is through finite source effects. Basically get this for free anytime you've observed a planetary microlensing event by virtue of a source trajectory going over a caustic and observing in multiple bands. You can measure theta e. Another way to do it that I'm not really going to talk about too much, but that in principle works the same way as what Fritz and Alessandro have been talking about, is astrometric microlensing. I was glad that Jesse told everyone to ask Alessandro about it during the break rather than me. A second mass distance relation revolves around measuring the microlens parallax. So here again, the relative parallax, which only hinges on the distance to the lens and distance to the source. So it boils down to the distance of the lens once you assume a distance to the source. Kappa is a constant. If you can measure this microlens parallax, now you have a second mass distance relation between the lens. There are a couple of ways to do this. One is by leveraging the orbital motion of the Earth around the sun, using the fact that if you have a long enough time scale, or if the orbital phase of the Earth over the course of the event works out just right, there will actually be acceleration of the Earth in the direction of observations, and this also induces asymmetries into the light curve. A second way is by having 2 widely spatially separated observers, and I'll talk a little bit more about what that means in a couple slides. And then the third mass distance relation comes out, or a third, if you're able to measure the lens flux. So if you can say, and this is mostly done in the near infrared, which is why I chose H, you can measure the H-band flux of the lens. We routinely have measured the extinction, and if you apply a mass luminosity relation, now this turns into a mass distance relation for the lens as well. So not really going to talk too much more about the Einstein radius. Again, we kind of get that one for free, but let's dive into microlens parallax and lens flux. So what I'm showing here, this is going to give an example of satellite parallax. So we're looking top down from the solar system, Sun is in yellow, Earth is in blue, and I'm showing for the Kepler spacecraft what the orbit looks like during K2's campaign 9. So this conducted a microlensing survey about 2 years ago. In the top left, for the dates of that campaign, well, I'm showing the dates up there. And in the top right, I'm showing the projected separation between K2 and the Earth in the plane of the sky as seen from the center of the galactic bulge, which is coincident with the center of the K2 campaign 9 survey superspan. So the left plot, the left panel here is going to be the same. And the right panel is, now we've just tilted it so that we're actually looking from basically the galactic plane, just about 5 degrees south. That's why it's slightly tilted. 5 degrees south of the galactic plane in looking at the solar system. So you can see this distance right here. This is the projected separation between Earth and K2. And I've also put on Spitzer, which was observing at the end of that campaign as well. So as you might have been noticing in the top left, or just inferring from looking at the animation, this projected separation ranges from about 1/10 of an AU to about an AU. And this turned out to be a very fruitful spatial separation for leveraging the separation to measure this microlens parallax effect. So now what we're doing is we're looking from the source's perspective, so again, from the galactic center, through an Einstein ring for a sample lens event, a lens system with a mass of a half solar mass at a distance of 4 kiloparsecs, so basically halfway between the solar system and the galactic bulge. And we're watching, tracing the path of each of these observer locations throughout the course of a sample microlensing event. So there's a couple of things to note here. One is that these different observer locations, again, Earth, K2 and Spitzer, not only are they different from each other, and we said earlier, for a single lens microlensing event, the magnification just depends on this angle, on this, this projected separation in the plane of the sky. But actually, even that angle changes as a function of time, and the relative angle changes. So if we smush this all together, what we're adding now in the bottom right is what is the actual observed light curve, magnification as a function of time. And we can see that there are two main ways that the light curves for each of these different observatories is going to look different. And again, this hinges critically on the fact that the separation is different for each of these two bodies. So the orange curve, which corresponds to Kepler, has the highest peak magnification by about a factor of 2, we see in the bottom right, over Earth. And that's because its separation is about twice as close in the course of the event. So you can see a difference in the peak magnitude of magnification. And this is also, it's a little difficult to tell on this plot with the stretch, but there's also a difference in the timing of the peak magnification, this T0 parameter. So this difference in the magnitude of the peak magnification and the timing, this is what allows you to measure or back out the microlens parallax. So this was done for the first time for a planet in 2014, a pilot Spitzer program. Here I'm showing the OGLE, that Polish observatory in Chile, light curve in black, and Spitzer data in red. And you can see that they both see this minor image perturbation. Just Spitzer sees it a little bit beforehand, and the structure is slightly different. And so this allowed us to measure, again, about a Jupiter mass planet here at about 4 kiloparsecs. And one thing I want to point out is that the precision on the microlens parallax is about 10 times better leveraging this spatial separation using this difference in the light curve morphologies compared to if you were just to try to back this out using just solely the orbital motion of the Earth. It drops from 22%, where it's the dominant source of the uncertainty budget, to about 2%. Pretty cool stuff. So now to talk about the other mass distance relation, talk about how do you actually measure the flux from the lens. I made a big deal about how a microlensing event doesn't actually critically hinge on the light from the source or the lens. In practice, though, as we're trying to play the stellar lottery, we're looking at very crowded regions on the sky. And so that means that in the PSF of whatever facility you're observing with, you're going to have the light from the source, which will usually be the dominant flux outputter. You'll also have the lens, and then you'll have any ambient interloping stars just in between that are not dynamically associated with either. Or if there are sources, companions to the source of the lens, those would also be blended. So one thing we do to try to isolate the microlensing target, the lens plus source, is use high resolution photometry using facilities such as Keck, especially locally. So here I'm showing about a 1.5 arc minutes on a side image from MOA. Being based in New Zealand, they routinely have 2.5 arc second seeing, so I've kind of cherry picked a pretty rough image. And the green dot here identifies the position of a true microlensing event. So we can see how this looks on UCURT, kind of sharpens it a little bit. This is an increase by about a factor of 2.5 in aperture. It's about 6 in collecting area. And then we can zoom in. So now we've already done a good job of kind of separating this microlensing target from some of the surrounding stars. We can do even better. So here's what this event looks like taken with the wide camera from NERC2, the AO camera on Keck 2. Already we've resolved out to a high probability all stars that are not associated with the microlensing event. And we can even zoom in a little bit more. And so here, let's switch from the wide camera to the narrow camera, kind of get a little bit better sampling. And so now we've zoomed in almost by a factor of about 10. Does anyone remember which one was the microlensing target? I don't either, but I put a circle on it. And I specifically put it off center. A lot of times people guess the middle one. No, it's not in the middle. It's this one here. So in the ground-based non-high resolution images, this light, this is the superimposed lens and source, was blended with a lot of these other stars. And so disentangling that is very, very useful. So the general procedure is you go from a ground-based image, here's the MOA images, zoomed in by about a factor of almost 10 again. And then here's how that resolution changes when you go from MOA to AO. And what this does is allows you to isolate the light from the microlensing target. Okay, I'm going to skip a couple of other slides. I'm going to leave you with W first. So two slides. So looking forward, people were asking earlier, what are things to look forward to in a given field? So the W first, the Wide Field Infrared Survey Telescope, recently entered into phase B. It's very exciting. And here on the left is a plot showing what are the currently proposed fields, target fields for the microlensing survey. And here's the galactic plane. On the right, and this is where your minds should just be totally blown, like get your helmets ready, is a light curve for planet plus star, where the mass of the star is about 0.3 solar masses, so an M dwarf. The companion is 2 times the mass of the moon. And you can just see this booming signal, booming at, basically H of 21 over here. Very easy to detect and characterize this event. Just to give you a sense of scale, a mass ratio, twice the moon around 0.3 solar mass star is a mass ratio of smaller than 1 in a million. So that's pretty awesome. And then I'll leave you with this plot. This is a plot also made by Matthew Penny. A lot of microlensers refer to it as the penny plot. He hates that, so please disseminate it. This is showing a simulated, so actual RV data points in black. This is planet mass as a function of semi-major axis. A realization of the simulated yields of Kepler in red, and the approximate sensitivity bound by the red line. And the same for the W first microlensing survey. So one of the powers of microlensing is to what we call complete the statistical census of exoplanet demographics, begun by Kepler and extending it out into the outer reaches of solar systems. If we wanted to do this linearly, it would look even more unfair. I'm not going to do that. The final thing I'll say is that the very lowest point here on this one detection per survey contour line, that's Ganymede. That's Ganymede. I'll take questions.
So would you see moons of Jupiter-sized objects?
Yeah, if you had, so again, it hinges on the mass ratio. So Ganymede around Jupiter would actually be a pretty feasible mass ratio to detect. I mean, with stepping down into Q, mass ratio of about 1 in a million. This is something that I think Alessandro was talking about earlier. The IAU is actually voting next week about a couple of things, one of which is the actual definition of a planet, and maybe using mass ratio, the L4, L5 transition barrier, as one motivating criterion. And as he mentioned, this is something that microlensing has kind of brought to the fore as far as confronting exactly what constitutes a planet. Is it something that's formation driven? Is it something that's observationally driven, et cetera? And there are a handful of discoveries actually already with objects, that would be analogous to Ganymede around Jupiter, or Jupiter mass planets around brown dwarfs. And so figuring out exactly what we do with these, it's a very exciting problem to have.
I'm going to call on Tiffany, but I think this might be a planted question. They're off with me.
Yeah. Yeah, so what happens, oh yeah, repeat the question, sorry. So the question is, let's say you have like Sun plus Jupiter, and Jupiter has Ganymede around it, that kind of a lens system, would we be able to detect it? So yeah, what happens is, let me see if I can go back quickly. It's a very good question. Where on the, so when looking at, I bring it up, yeah, when looking at the caustic topology for a given lens system, so I'm just showing for a close topology, but this kind of doesn't matter. You always have at least one central caustic, and then you have 0, 1, or 2 planetary caustics. And we refer to them as planetary, even though they could be due to a companion that's not a planet. But you have central one and then additional caustics. What happens when you start populating a lens system with more than 2 bodies is you'll get additional planetary caustics according to the separation between that additional body and the host body. And it will also affect the structure of the central caustic here. So for a 2-body lens system, they're closed curves, they're non-intersecting, and that changes. All that kind of goes out the window when you start adding additional bodies. So you don't necessarily just need to have some contrived source trajectory that would, you know, take you over a planetary caustic for one of the companions and then a planetary caustic for the other one. If you probe the central caustic as well, you can get a number of bumps and wiggles or just changes in your magnification structure where you know that there must be more than 2 lens bodies. Yeah, it's actually, if people are looking for very hard and also interesting problems to solve, 3-body lens systems are a pretty big open question right now, both in terms of kind of the amount of computational power, and there's several systems that have gone unpublished because they're probably 3-body, but we don't really know how to do it in a fast and efficient method.
What are the signals that are hardest to disentangle
So the question is, what kinds of signals are difficult to disentangle for microlensing? There's a couple of different classes. So if you're trying to do targeted follow-up observations on kind of a quick time scale as a microlensing event is evolving, the kind of initial rise of microlensing events can look like a flare from an M dwarf. Sometimes even caustic entrances or exits can look like CVs. Underlying stellar variability, it's difficult, but that's actually something you can kind of model and remove. There are some other kind of intrinsic difficulties that Jen will talk about in the next talk that are kind of related to this as well. What type of stars are the host stars? So in general, some people refer to M dwarfs as the vermin of the universe. I actually really like them. Based purely just on number density in the galaxy along the line of sight, kind of regardless of what your IMS slope is, M dwarfs are the most common types of hosts. Yeah. Good question.
Let's thank Calen again.